Good morning, Max. Max, unmute.
Hello.
Yep. Good morning to you.
Good morning.
So, I figured what we could do today, if you don't have any specific problems,
Okay.
is give me a general problem, and I can find some problems of that nature.
And then maybe I could try and work through them, and we could
Yeah.
do that.
Yeah.
Okay.
I mean, the best case is if you have the problems, because only you know the exact degree of difficulty and the stuff that you've been studying.
Here's the thing. My teacher, basically, here's the deal. If it exists and it was a topic, if it was within the general topic of anything we've learned, he's going to give it to us in the test. It doesn't matter how hard it is.
Okay. All right. Well, one thing you mentioned last time was factoring quadratics that have coefficients other than 1.
Right.
I've got some of those. Why don't we start there? Okay. Because, in fact, there's few subject matter that are more important in algebra than being able to factor quadratics. Hold on. Go ahead. Get started on the methodology.
So I can... No, I can't. Okay. So 2x squared plus 7x.
Don't try to do the whole thing at once.
Right.
In other words, do step 1, which is to split up the 2x squared.
So I'm going to do 2x and 1, because that's really the only factor.
2x and x, correct. And as you do this, always in your mind check to make sure that times that is equal to what you started with. In other words, had I really written down what you said, well, 2x times 1 does not equal 2x squared.
Yeah, I meant x.
Okay. But nonetheless, that's always a good process, is to check as you go. What's the next step?
The next step is to factor the rest of them. So 7x.
Actually, I find these things a lot easier if you do the second step as determining what both signs are.
Well, they're both plus signs.
Okay, that's step 2. Now, once you get this far, the rest of it's relatively easy. How many factors of 3 are there?
2. Oh, there's 3, I guess.
Well, there's one pair of factors, yeah. So our answer either has to be 1 and 3 or 3 and 1.
Right.
And all you have to do is try both combinations and you'll get, what is it? What goes here?
So 3.
Okay, if I try that, 3 and 1, now I need to check to see whether that indeed produces the middle term of 7x. How do I do that?
You could, check it by multiplying the 3 to the x and 3 to the 1.
Well, the 3 to the x and the 2x.
And 2x to the 1.
In other words, multiply the insides together, the outsides together, add them together. That needs to be your middle term. What do we get when we do that here?
3x and 2x. It makes 5x. So that's wrong.
So we didn't do it right. So let's go back and try the only other alternative, which is 1 and 3.
So then you get 1x and 5 and 6x. So that's right.
Okay. And that's basically the way you do those problems. And
then if you can factor out a...
Go ahead.
If you can factor out a common term, you should do that first, right?
Yes, always. And in fact, I'm going to give you a mixture of problems. I'm going to give you some where that needs to be your first step. I'm also going to give you some that are difference of perfect squares. Factor that.
That's 9x plus 1, 9x minus 1.
Correct. And they're going to mix those up. It's the first step here.
Factor out the 2.
Okay. Leaving.
It leaves. Wait, I don't know. It leaves 81.
Right. Taking half of an even number is relatively straightforward.
Yeah.
You have to take half of that number and half of 16. So,
yeah.
81,
That's 81.
X squared minus
X squared minus
1. And now, notice now you have difference of perfect squares in there.
Right. So then it's 2 9x plus 1, 2 9x minus 2 9x plus 1, 9x minus 1.
Correct. Now, when you have difference of perfect squares, you can do the whole first term first, because you know the second term is, you know, you don't have to figure it out. It's just the opposite sign.
Right.
So when you're doing difference of perfect squares, I don't do it step 1, 2, 3, 4. I do it all at once.
Right.
Okay. Go step by step.
So first, factors of 3 are 3 and 1. So it's going to be 3x on one side and 1x on the other side.
Okay.
Your signs are going to be plus signs. And then your factors of 10, there's a few. So I guess try the ones that are closest together is 5 and 2.
Okay.
So if you have 5 and 2, the factor is 17. 5. So 5 and x, and then 3 and 6. So that's not right.
Okay. When you see a problem here, there is a little bit of a clue. That's a big number, right? Relative to all the other numbers in the quadratic.
Right.
And the only way we're going to be able to produce that big number is if we have our biggest factor, 5, multiplying our 3x. So one place to start there might be there. Because
okay.
I know I have to get a big number to get this middle term.
Yeah, that's true. So then 5 and 3, so that's 15x and that's 2x. So that's right.
So that works. Right. And notice that when you're done, you don't need to check this term here or this term here. You really don't. Part of the process of factoring it was factoring those two terms. So we're pretty certain we've got those terms right. The one term that you have to get right that's not, the toughest one to get right is that middle term. So really you only have to do the insides and outsides to check it.
Right.
And of course, in the process of solving this, we did the insides and outsides, so we're done there. Okay, now let's do a little harder one.
Okay. So, again, the factors are going to be 3 and 1.
3x and x.
Right.
Okay.
Sign's gonna. And then your signs are going to be 1 plus and 1 minus.
Okay, but in this case, plus minus is not going to be the same as minus plus.
Right. I never knew how to tell the difference of by looking at it.
The difference is if these coefficients are different, then there's going to be a difference. If they're both 3, let's say we had 3x and 3x, well then plus minus is the same as minus plus. There's no difference.
Right.
But in a case where the coefficients are not the same, then you have to allow for both. And I do it this way. Okay? Now, factors of 11. We're lucky because there's not very many of them. In other words, the harder difficulty problems would be if that was a 12.
Right,
All kinds of factors of 12. So it just increases the amount of trial and error you have to do if there's a lot of factors of that number.
And then 32 is big. Correct. So I'm going to assume that we have to multiply our 11 by our 3x.
Okay, and also the 32 has a plus sign in front of it.
Right, so it's
So
got
a
to be
good
positive.
place to start would be right there. 11 there and 1 there.
So 3x, what's the 33 minus 1 is plus 32. So that's right.
Got it. We won't spend the whole time on this, just till I feel like you're at a point where you get it. And I think you're getting close.
Okay, so if they're both minus, then one of them still has to be positive, right?
Well, start step 1.
Okay. So step 1 would be 2 and 2, I guess, because they're closest together. 2x and 2x.
We'll try that one. It may end up being 4 and 1, but we'll have to see. What are the signs?
Minus?
Signs have to be opposite. That's all you know. You cannot produce a negative 27 as a constant unless your signs are opposite.
Okay. But because they're both 2x, it doesn't matter which is which right now. So just put a minus on the first one.
Well, I can do it either way. And I only need to do 1, because plus minus is going to be the same as minus plus, because both of these numbers are going to be multiplying the same number. They're both going to be multiplying at 2x. Now, if we have to go back and change it to 4x and x, then I'm going to have to use my notation of plus minus over here and minus plus over here.
Okay.
But for the moment, we'll see if this works. Now, factors of 27. Let me just show you a little technique that I use for finding all factors. First, I try to divide this by 2. If I can divide it by 2, I do so, and I multiply that by 2.
Okay.
In other words, if it was 28 and 1, my first step would be to go down to 14 and 2.
Right.
And 7 and 4. You can keep going until you reach the bottom. Okay? Right. If this number is not divisible by 2, I try to divide it by 3. Well, I can do that. And if I divide that by 3, I got to multiply that by 3. Still can't divide it by 2. I could divide it by 3 again, and I get down to that and multiply that by 3. In other words, now I'm producing the same factors.
Right.
So I'm relatively confident that I've got both my sets of factors. Again, 13 is a small number relative to 27.
Right, so we might want to try 9 and 3.
Probably not going to need that set of factors. 27 times 2x is going to get you to 54 immediately, and there's no way you're getting back to 13. So it's most likely 9 and 3. Well, again, I'm not sure which needs to go which. We got a negative sign on the middle. So let's put the bigger number with the negative sign and the smaller number with the positive sign. Does that
work? So 6x and minus 18.
Doesn't work. I know that 27 and 1 doesn't work either.
So we have to just switch 3 and 9.
No, I got to go back. And I got to restart the problem using 4x and x. Because remember,
because
I had
9 and 3. 9 and 3 would be the same no matter how you put them, right?
Well, that's true. I still got to deal with the factors of 27. But now I have a plus, minus, and a minus plus. Okay? And I'm still going to start with 9 and 3. And 9 there and 3 there. It's useful to know the size of the number that it produces.
Right.
This would produce a plus 9 and a minus 12 or a minus 3. That's not even that number. So I don't need to try 9 down here and 3 over there. It's going to produce the same number, just a different sign. So let's try 3 and 9. Well, 9 times 4 is 36. That's awfully big. There's no way I'm coming back from that. So 3 and 9 don't appear to work either.
So it's going to be 27 and 1?
No, I don't think that's going to work either. In other words, I certainly wouldn't want to multiply the 27 times the 4. So if it was 27 and 1, it would be something like that. And notice that gets you back to a 23x, but not a 24x. Now, I pulled this from a set of questions that said, factor the trinomial. If the trinomial cannot be factored, say so. This is a trinomial that cannot be factored. Okay?
Okay.
Now we're going to prove it. In other words, if I actually could have factored it, and I just didn't find it, when I use the quadratic formula to solve this, I'll get whole numbers, which will tell me that I could have factored it all along, I just didn't see how to do it.
Right.
So the next step would be to go into the quadratic formula. Remember what it is? That's something you want to memorize if you don't have it memorized.
B plus or minus.
Okay, so let's plug it in as we go.
13, negative 13.
No, you were right. Let's do the general. Minus b, what is it?
Plus or minus the square root of 4a plus b.
B squared minus 4ac.
Oh.
That has other meaning. That actually is also called the discriminant. It has its own name. And I'm talking about just the part that's inside the radical sign.
Okay.
A lot of times, they will begin quadratics by determining what the discriminant is. Because this will tell you all by itself whether you have real solutions or imaginary solutions. Okay? And so that's why it has its own name. And that makes it a little easier to memorize, is the fact that sometimes you have to deal with just b squared minus 4ac.
Right.
And the whole thing's over 2a. And also, remember, the formula for finding the vertex, if it's in standard format, is that part of the quadratic. So that should help you memorize the vertex formula and also the quadratic formula by knowing that minus b over 2a. Now let's plug it in. It's minus b. What's b?
13.
Correct. B is minus 13, so minus b is 13.
Plus or minus the square root of negative 13.
It's b squared, so here we don't really care whether it's positive or negative because it's going to turn positive. Right. So that's 169. And then I always recommend doing this. Don't try to do this part in your head because it's just begging for a mistake. And you'll see why. Because you end up with a bunch of negative signs, and this negative sign is subtracting. That is a negative sign. So they're not even the same kind of negative signs.
Okay.
Okay. Now, I'm going to suggest you always do that next. In other words, there's a method to my madness here. Rather than trying to do minus 4 times minus 27, do this part first, come up with a number, and then subtract it from your first number. you have a calculator?
Yeah.
It's 16 times 27.
16 times 27 is 432.
So there's the discriminant right there. And that's negative. Okay, because it's negative, it tells me the only solutions to this problem are imaginary. There are no real zeros. If I graph that parabola, it will not cross the x-axis. There will be no x-intercepts. And I know all of that by just looking at the discriminant. I haven't even finished figuring out what the answer is yet. What's that number? What's 169 minus 432?
169 minus 432 is negative 263.
All over 8. Well, 263. You've had imaginary numbers, right?
Briefly, yeah. Like I.
Tell me what this is. What's the square root of negative 16?
Oh, I thought you were still right. I guess that froze. Square root of negative 16 is 4i.
Correct. In other words, always, if you have any questions about any of these, the best thing to do is to take out the negative 1, leaving behind the plus 16, and then that's always I, and that you have no problem doing that. Okay?
My teacher said that won't be on this test specifically, so that's good.
Imaginary numbers won't be? Okay, well, let's not spend any more time on this then. I don't know if there's any factors of that number or not. We'd have to spend time doing it. But if not, then your final answer is going to be there's one x, and the other x is 13 over 8 minus root minus 263i.
Right, you have two answers.
Clearly, coming up with these answers, it's no wonder we couldn't factor it. Not only was it not integer factors, it was imaginary. So, all right. Well, now see, there's a problem. I might have spent a lot of time on something that's not going to be on your test. All right. I got some here that factor for sure that I know of. Although there's a lot to be learned by that problem we just did.
Yeah, there is.
In other words,
he never said that he's always going to give us ones that are factorable on the test.
Okay.
But if we don't have to go into that much detail.
Right. Of course, the ultimate determining factor is how many minutes do you want to spend trying to factor it before you go into the quadratic.
Right, that's true.
If you're going to have to use quadratic, the sooner you use it, the better.
On the last test, we weren't allowed to use it.
Oh, okay.
We had to do it by factoring.
So that might not even be on this test, is the quadratic. Okay,
right.
Good. Okay, what am I going to do here?
So here you're going to factor out a 5.
Okay, that's always the first step, always, is to seek a greatest common factor. And like I said, when you are factoring it out, make sure, in other words, in my head, I did that. That's correct. I did that. That's correct. And I did that. That's correct.
Right.
Okay. Now, this is a first order factoring problem.
So, x plus something, and then x minus something.
Okay. So the second step is done. I don't even look at the numbers at this point. I just completely figure out the signs, because now you have the problem 2/3 solved, 3/4 solved. What are the factors of 2? Now you can actually use the rule that factors of 2 that subtract because of that negative sign to the coefficient of the x term, which is a 1. Okay, so that's the logic you use on first level. We'll do another one of those, just make sure you got that down.
Okay.
But
would it be
it's
1 and
not
negative?
add to 1, it's subtract to 1 because of that negative sign. If that sign was a positive sign, then it would be factors of 2 that add to whatever that is.
Okay, so it's negative 1. So it's x minus 1 and x plus 2.
Yes, and you put the larger of those two factors. We know the factors are 2 and 1, but we still have to decide which sign to put them with. Well, we're going to put the larger factor with the sign of the middle term. Okay, let me just do one other here that is useful to do. Let's do this one. Get you started.
Okay. So it's going to be 1 plus and 1 minus.
Now what's the rule? Factors of 27 that do what?
Factors of 27 that add to 6.
Factors of 27 that subtract to 6.
Oh, okay.
Okay, that sign is key in two places. That sign allows you to determine both of your signs, and it also specifies the rule that you're looking for. You're looking for factors that subtract. And it's not necessarily to the number plus 6. It's factors that subtract to 6. In other words, I could change the problem to this. Let's do that. Okay, so far everything's still the same. But now I need factors of 27 that subtract to the number 6. Well,
that's 9,
3. Which side's the
so it's going to be negative 9 and positive 3.
Correct. Okay, good. That's the logic I wanted to go through at least once.
Okay. So do you think we should move on from factoring now, or do you think?
I think so. I think you. Well, let's try one other, just because. Let's solve one equation at least.
Okay. Oh no, never mind. Wait, this is equals?
This is an equation, which is different than what we've been dealing with. We've been dealing with factoring expressions.
Okay, so I'm going to...
Factoring expressions is always just a first step towards solving equations. In other words, the ultimate goal is to be able to solve equations. Every one of those expressions that we just dealt with, I could set that equal to 0, and then you have an equation that you need to solve by factoring.
Okay, so then subtract negative 16x squared. Subtract 16x squared from both sides.
I can do that, but that's going to give me a negative coefficient when I get it over here to the right side. Dealing with negative coefficients is really a trick. You don't ever want to do that. Always turn the problem so that the coefficient of the squared term is a positive number.
Okay, then subtract 8x and add 1.
And that leaves 0 over there. Now we have an equation that we can solve. Go ahead, factor that.
So it's going to be, I'm going to try 4 and 4 first. Because they're closest together and because 8x is also a...
Right. It's pretty clear what the answer is going to be here. What's both my signs?
Both your signs are minus?
Both of them are minus, exactly. This tells you that they're both the same. This tells you they're both minus.
Okay. So if it's positive on the one that's not a coefficient of x, the last term on C, then that means that it's going to be the same?
Yes, that means the same. If it's minus, they have to be opposite.
Okay.
That's the second step, basically. Although when we know that they have to be the same, they can still either be plus plus or minus minus. We determine which by looking at the sign of that term.
Right.
Clearly, there's only one set of factors of 1, and that works. Gives you minus 4x there, minus 4x there, gives you minus 3x. Okay. So the reason I wanted to do this was because it was not set out in standard format. It was something you had to put together before you could factor it.
Right.
Okay, we've done greatest common factor, difference of squares, first level factoring, and second level factoring. Let's go to a different subject. Absolute values is also in the same chapter.
So can we cover both doing them and graphing them at the same time?
Yes. Do you want to go? Shall we go back and graph? Let's graph some quadratics.
Okay.
In fact, graphing parabolas. Let's see if this. Yeah, this is a good one. Okay, this one is in standard format. This one is in what kind of format?
That one is in I know it. It's Vertex format.
And the third one
is in factored format.
It's in X-Intercepts format.
Oh, okay.
Okay, so let's graph. Let's see, for me the best way to graph it's going to be like this. So when it's in standard format, I got a bunch of choices, and I mean a bunch. I could draw a table of x and y values, right?
Right.
Connect the dots. I know it's going to look like a parabola, so it won't be hard to connect the dots. So that's one way. That's the way we don't use very often because it's so laborious. The other way is to immediately figure out the vertex by using minus b over 2a.
Minus b, oh, okay, yeah.
Okay, that'll give you the vertex, and then you can go from there as to figure out the x-intercepts. Let's plan on factoring these as x-intercepts and the vertex if we have x-intercepts. Don't always have x-intercepts, in which case you're going to use the y-intercept. But you always have a vertex.
Minus b over 2a is the vertex, right?
That's the x-coordinate, or the line of symmetry. Have you used that term, line of symmetry?
Yeah.
Okay. Line of symmetry is the same thing as the x-coordinate of the vertex, and it's minus b over 2a if it's in standard format.
Right.
Let's use this technique this time. So tell me what minus b over 2a is.
In this case, it's just going to be 1, but it's 4 over 4.
Okay. So the x-coordinate of our vertex is 1. So at a very minimum, I can draw a dotted vertical line through x equal 1. And we know that the parabola is going to be symmetrical about that line.
Right.
Now, let's find out the y-coordinate of the vertex. And then we'll have a point we can put on that dotted line. How do I get the y-coordinate?
Plug in x to the original format and see what your y is.
What do you get?
You get 2 minus 4 plus 2, you get 0.
Okay. Now we know a lot.
Now you know our vertex, right?
Yeah, we know that it's at 1, 0. So it's right there. It also,
so it's not going to be any other x.
It also opens up if the vertex is lying on the x-axis then it's going to have exactly one real solution. It's not going to have two x-intercepts, but it's going to have one x-intercept.
Right.
In other words, this thing, to find two other points, what's the easiest thing to do? In other words, it's going to look something like this, or, you know, I've got to still determine its shape,
right,
whether it's skinny or fat. Okay.
So I would set y equal to 0.
Well, notice that y is equal to 0. When you set y equal to 0, is all you're going to come up with is x is 1. We know that this point right there, 1, 0, is on that function.
Okay.
So
I'm going to try my y
doesn't help here. In the same way that if we saw that the vertex was way up here and that it opened up, there is no y equal to 0 if this is my graph. There's no value of x where y is ever equal to 0.
Right.
So you don't want to use that strategy unless you know that the parabola crosses the x-axis once or twice. If it's only once, then we already know the vertex, so there's no point in going back and resolving that problem. However, there is another point on this parabola that's quite easy to figure out. There's always a y-intercept. And the y-intercept is always this number.
It's 2?
Well, it's where x is 0. No matter what the rest of the quadratic looks like, when I plug in x of 0, that term disappears, and I'm left with 2. So I know that point is on my curve. 0, 2. So,
and then you also know.
Go ahead.
From that,
I'm just going to draw half of it. Yep. Go ahead.
You know that 3, 2 is also there.
Not 3, but you're close.
Not 3. 4. Wait, 4.
It would be the same distance. How far is this thing from that line of symmetry?
It's 2. Oh, it's 1. So it's 2, 2.
Now I can draw the rest of the problem. And like I said, 3 points determine everything there is to know about a parabola.
Right.
Okay. Let's move to this one. Now, there was another way to do this one. I could complete the square, or I could try to factor it and make it look like this over here. Because there's one big advantage when it's in X-intercept format. You know exactly where to draw the X-intercepts, and halfway in between them is the line of symmetry. And you know it opens down because of that negative sign. So this is a pretty useful format for graphing. But let's just go through one at a time here and deal with whatever format they're giving us. So what's the general format for the vertex format?
The general format for this is x minus...
There's an a in front.
Oh. A x minus b squared.
H.
Oh, it's h, right. Plus k.
Good. Okay. That's what we're looking at here. There's our a is minus 1/2. Our h is positive 3. And our k is positive 5. Okay. So, I can immediately put the vertex at 3, 5. Right there. Furthermore, I know it opens down because of that negative sign. So it is going to go down, telling me that I've got x-intercepts.
Right.
How do we solve for them? And if, I'm going to say this, if there are x-intercepts, you always want to get your other 2 points from those. That's not a requirement in math, but the two next most valuable points are where it crosses the x-intercept, not so much the y-intercept. You could figure out the y-intercept and finish graphing it from that, but the x-intercept, your teacher's almost always going to want that.
Right.
So, how do I get the x-intercepts?
Well, in this case, 3 and 5, oh, yeah, it's going to be 3 and 5 are your x-intercepts.
No, that's the coordinates of the vertex. In other words, my parabola looks something like this.
Right. Isn't it 3 plus 5? Isn't that your...
No. How do we get the...
Oh, no. You set y equal to 0.
There you go. So, 0, I'm going to set equal to this. Y 0, and I'm just going to solve this equation. There's only one variable in it, x.
Right. So then you subtract 5.
Okay.
Five equals negative 1/2 x minus
the next
3.
best way to solve this problem. What's the next best step in this algebra equation?
To multiply both sides by 2?
Yes. In other words, usually the order I have is getting rid of denominators and getting rid of parentheses.
Right.
Well, in this case, I want to get rid of my denominator first. Then I can get rid of my parentheses. And I can get rid of my denominator by multiplying both sides by 2 or negative 2.
Negative 2.
Negative 2 works better. Gives us positive numbers everywhere. What's the next step?
The next step is getting the square root of both sides.
Correct. Notice that the next step is not to distribute that. In other words, I don't want to square that.
No, you want to get rid of that.
When I square that, I'm going to have to bring the minus 10 over there and then go through the whole quadratic factoring stuff. By far the easiest way to solve this is to take the square root of both sides.
And to get from standard form to this form is you complete the square, right?
You can, yes. Yes. To get to vertex format, you have to complete the square. We could have taken that first problem and done this. And done that. Yeah, completed the square, and that puts it in vertex format. But you'll notice that even when it's in vertex format, you know where the vertex is, but it doesn't make solving for the x-intercepts any easier.
Right.
Best format is this format. This format gives you the x-intercepts immediately, gives you the line of symmetry, which is halfway in between. That line of symmetry gives you the x-coordinate of the vertex.
So once you're at the square root of 10 equals x minus 3, they're kind of...
Notice that's not the answer. Remember what I said. Whenever you solve an equation by taking the square root of both sides, begin your answer with plus or minus.
Oh, plus or minus the square root.
Right. So, x minus 3, I'm just going to put on the left side just because it's easier to think about it in terms like that. So that's the next step after taking the square root of both sides.
Then you add 3.
Plus or minus is critical. Notice I've got to have 2 x-intercepts. I know that parabola is going through there like that and there. So to come up with only one x-intercept would be a real problem. Well, now I add 3 to both sides, and I've got both my x-intercepts right there.
What 2 numbers is the square root of 10 between? Sort of thing.
3 and change. In other words, 3 squared is 9, 4 squared is 16, so it's got to be a number very close to 3.
So it's going to be somewhere between 3 and 0.
Call it 3.1. No, it's got to be above 3, because 3 squared is 9.
Right, but when you subtract it.
Well, okay. In other words, this has 2 answers. One is 3 plus, we'll call it 3.1, and the other is 3 minus 3.1. So this is the plus one. So that coordinate is about, I'm going to round off here, 6.1 comma 0. And this coordinate I got on the wrong side of the y-axis. It's actually right there. It's slightly negative. It's negative 0.1.
Right.
So now, when I draw my parabola, I can draw it precisely. Got to go through those 2 points.
And then that's your answer.
And that's my graph, yeah. And now some teachers, I've had some teachers or students say that their teacher always requires 5 points. Well, if we needed 5, does yours? I mean, we won't even go into that if your teacher...
No, he's okay with 3 points.
Okay, because the 5th point's always going to, that's pretty easy to find, and you know that one's symmetrical with it. So finding 2 other points isn't hard if you use the y-intercept. And like I said, there's always a y-intercept. Although it's not completely clear what it is here in vertex format. It's not 5. It's only that constant if it's in standard format. In other words, that's in standard format, so I know the y-intercept is 2. But the y-intercept here, I would have to substitute 0 for x and solve that out.
Right.
Okay.
Which wouldn't be that hard, but it's just...
No, but it's not readily apparent what the y-intercept is from looking at it.
Right.
Okay. And the general for x-intercept is? Still that A. And they don't use H and K, they use P and Q. Just to kind of distinguish them conceptually. In fact...
So it's the opposite of whatever is in the, like what they gave you. So we know that this one turns down.
Correct, because that -1. But there's a lot. Yeah, in other words, we're looking at negative times x minus 3 times x plus 1. So where are my x-intercepts?
Your x-intercepts are going to be a positive 3 and -1.
Where's my line of symmetry? Which is the same thing as where's the x-coordinate of the vertex?
At x1.
You don't always need to draw that dotted line, but it tells you that my x-coordinate of the vertex is somewhere on that dotted line.
Right.
I only have one other thing to figure out. I know it drops down, so my vertex has to be somewhere up here. My x-coordinate is 1. What's the y-coordinate? Plug it into that right there. Plug in the x value of the vertex, which we know to be 1.
1 to the equation.
To the equation, and the equation is this one right there.
Right, so it's going to be...
We don't need to do anything else to that equation. Just plug in 1 for x, and what do you get?
-2, well, it's like -1 times the quantity, -2 times 2. So it's going to be positive 4.
So the coordinates of our vertex are 1, 4. And we know everything necessary to graph it.
Okay, it's not that difficult.
No, as long as you're familiar with all 3 formats, and when you're given this format, that's the only thing to use. I can't imagine a method that's easier than what we just did.
Right.
Okay, when you're given vertex format, the way we did it is the easiest way. The only one that there might be multiple ways and one might be easier than another is when you're given it in standard format. Right. And then generally you have 2 choices. You can complete the square, which puts it in this format. You know what?
Which he really makes us do.
Let's do that. Let's complete the square on this first one. Just because it's got a little trickiness to it. Okay. In other words, we're going to complete the square so that it is in this format. That's our goal. In other words, we're going to immediately know the vertex after we complete the square. It's the first thing I need to do.
2x squared minus 4x plus 4.
Okay, you cannot complete the square until this coefficient is 1.
Oh.
So the first thing you got to do is factor out the 2. And it doesn't matter whether it's divisible or not. Yeah, I could make a 3 there. Okay? I would still have to factor out that 2, and this would become 3 halves.
Okay.
Okay? We'll leave it at 4 to make all the math a little easier. But factor out the 2 and separate. In other words, I'm only factoring out the 2 from this part of the equation. I'm not going to factor out the 2 that's over here. I'm just going to set that way over there like that, and I'm going to leave room with my parentheses to complete the square. Okay? So that's my first step. Make sure you don't factor out the 2 from over here. Now I can complete the square on what's inside because I have a coefficient of 1. That's the only thing necessary.
So then it's going to be...
It's always adding.
Plus... 1?
Half of this squared. And you don't care if it's negative or positive. It's half of that number squared. Because when you square it, it eliminates the relevancy of the sign. Okay? And because I wrote in something into this equation that wasn't there, I can't just do that. I've changed the equation when I wrote plus 1. In other words, at this point, the equations are identical. So now what do I have to do to make them stay identical?
Minus 1.
How much did I add to the right side of the equation when I wrote that 1 in there?
Nothing.
I added 2.
Wait, what?
I'm multiplying that thing by the number 2 that I factored out.
Okay.
So I actually just added 2 to the right side of the equation, which means I have to subtract 2 to balance it out. Now everything is the same. In other words, everything you see here is equal to up here.
So then on the outside there's going to be a 0. There's not going to be an intercept.
Correct. So we're going to write this. How can I write this now? You're always going to be able to write that as a linear term squared. That was the whole reason you complete the square.
So it's 2 times x minus 1.
It's always the sign of the middle term.
X minus 1 squared.
Whatever you got when you took half of that, that's what you're squaring. Plus 0. So now where's my vertex?
Your vertex is at 1, 0.
Correct. And what's my X-intercepts?
Your X-intercepts are, when you know that your y is 1, you said it equals... Oh, no. No. Divide by 2.
Okay.
So you have 1/2 on the other side?
No. 0 divided by 2 is 0.
Oh.
I don't have anything on the other side. I have x minus 1 squared equals 0.
But then we have a problem, don't we? Because you're going to have...
Not really. If you remember the answer we had on this, there was only one x-intercept.
Right.
Take the square root of both sides.
You can square root 0?
Uh-huh. You can take the square root of 0. You can't take the square root of a negative number, but you can take the square root of 0. So I get 0 equal x minus 1, giving me only one answer.
1.
Remember, this thing looked like this. There was only one x-intercept.
Right.
So I don't know. You know, it's up to you to decide whether you want to use the complete the square method or the minus b over 2a method. I think they're about equal in terms of level of work. So whichever one you feel the most comfortable with is going to be the one that you're going to be the most accurate with.
Right. Except I think on the test he's going to make us use completing the square.
Okay. This is the only one where you really have much of a choice. These two formats are pretty much directing you on how to do it. Okay, so we've talked about graphing quadratics. Let's see if I have any absolute value graphing here. Not that it's labeled, but I've got plenty of problems in my book that we can do graphing of absolute values. Generally, graphing absolute values, now you gave me a problem the other day that wasn't the case, but if it is a translation of this, then that's the best way to figure out how to graph it.
Right.
Okay. In other words, if I gave you y equals 2 times the absolute value of 3x minus 4 plus 5, that is a translation of that.
Right.
Let's go through each one. What does this do?
Changes the slope.
Nope. It's a vertical stretch factor. In other words, if I graph the basic one, always graphs like that. You're right, it does change the slope. But in terms of, you've studied translations of polynomials, haven't you?
A little bit.
Really? So you're not that familiar with the terms vertical stretch, vertical shrink, horizontal stretch, horizontal shrink?
I know them. No. I mean, I know the words, but I don't really know what they mean.
Okay. Let's cover that, because I'm not sure how else to teach how to graph absolute value functions without knowing what these do. The fact that it's a vertical stretch factor because it's in front of the equation, it's not inside it. Okay? And a vertical stretch factor, any point that would have been there is going to be twice as far away from the x-axis. If I have a point here, it's going to be way up here when I multiply it by 2. And the effect of that is you end up with a skinnification of your graph. In other words, it increases the slope as you would expect it to. Although this number has, well, let's go through these one at a time rather than all at once. This 3, that is inside the function. That is a multiplier of the x. That is a horizontal shrink factor. It's shrink when it's greater than 1. It's stretch when it's between 0 and 1. So if I had just this, it would be a shrink compression, a shrinking horizontally. Notice that if I shrink that by pushing on the sides of it, it ends up with a skinnification of it. So when this multiplier is greater than 1, it acts as a horizontal compression. When this multiplier is greater than 1, has the same effect. It's a horizontal compression, but we call it a vertical stretch.
Right.
Vertical stretches and horizontal compressions actually change the shape of the curve in the same way. Okay? Now, let's go through them exactly one by one. If I had this, what's the 4 do? Or then minus 4?
What? Wait, I'm sorry, what did you ask?
If I have just this, I want to do these changes with these translations one at a time.
Okay.
So if I had just this, what would happen to this curve?
You had just that, it would change where the vertex is.
Strictly a horizontal shift. Notice the word shift does not indicate a change of shape.
Right, it just changes where the vertex is.
Exactly. It's going to change everything horizontally. Which way?
Right. It's going to move it to the right.
By 4. So
by
I
4.
bring it over to there, and I would have exactly the same slopes, and it would just look like that. Okay? And now finally, the last thing that we would do, not the last, but if I had this where I'm adding a number, again, outside the function, not inside it, what's that called, and what does it do?
That's a vertical shift.
Okay? And plus goes up, minus goes down.
Right.
So that would look like that.
Right.
Combining them all together. Well, let's cover the other two. Just one moment. If I stick a negative sign in front, what's that look like?
Upside down.
And if I stick a negative sign inside, what's that look like?
The slope is opposite.
That is a reflection over the y-axis. The first one is a reflection over the x-axis. That's what made it look upside down. Right. This one is a reflection over the y-axis, so it doesn't change anything. It looks exactly the same. Yeah, it's exactly the same. But it is one of the other things you can do. In other words, there are 6 things you can do. You can reflect over either axis, depending on whether the negative sign's in front or inside the function. Okay. And you can vertically stretch, horizontally shrink or stretch, horizontally shift, and vertically shift.
Right.
And if you do them all in the same function, let's say I had something like that. I'll do everything but the reflection over the y-axis.
Okay.
Now, the one thing that's very important, if you have minus signs involved, is that you do your reflections first. It matters. If I do my vertical shift first and then reflect, notice I'm going to get something different. In other words, if I did just the vertical shift first, it would go up to there, and then I reflect, it goes way down to there, right?
Right.
But let's do the reflection first, which goes to there, and then the vertical shift brings it up. So it's a completely different place on the graph.
Which one do you do first?
You do the reflections first, always. And it doesn't matter which one. If you have both, in other words, if I had a negative sign there, you would do both reflections and then everything else. It doesn't matter which order you do your reflections in, but relative to each other, but you want to do them first, and then it doesn't matter what order you do everything else in. So the first thing I'm going to do to graph this is reflect it and vertically stretch it. See that?
Right.
In other words, I took care of that whole thing right there. Okay? Next thing I'm going to do is compress it more, because that number is greater than 1. So now it looks like that. Now I'm going to move the whole thing over to the right 4 units. So now it's like that. And then I'm going to move everything up 5 units. So you end up with that. Okay. Just do them one at a time. And just make sure you do your reflections first. That actually should cover, I would have thought that that would have covered graphing all absolute values, but you gave me one last time that I hadn't seen before, which is interesting.
It was y equals x minus the absolute value of x.
Now this is not just a translation of the elementary function. There's no way I can translate that and come up with this. So I have to graph this in a different way. I have to graph it piecewise.
Right. And I was messing around with it yesterday, and I realized that if you just start plugging in points for x, you can graph it.
Yeah.
Like that's all you need.
Absolutely. Plus and minus points. I mean, you want to plug in plus and minus numbers for x.
Right, because it's an absolute value.
And that is basically what I did when I broke it up into when x is greater than 0, this function is equal to 0 because it's x minus x.
Right.
Okay, but when x is less than 0, then I end up with 2x. So now, at least I don't have an absolute value to worry about anymore. In other words, instead of this that you gave me, this is what I'm graphing. F of x, it's this piecemeal function.
Right.
And you know how to graph piecewise functions, right?
Right.
Always start, actually, usually I've got these backwards. Usually you start at the negative infinity at the top. I got x being greater than 0. I should have switched these two around and switched those two around. It's probably why I got confused yesterday, because I didn't. In other words, I always tell people start there and start from negative infinity. Well, you can't start from negative infinity if I'm starting from x greater than 0.
Right.
So I really should have this thing looking like this. It's equal to 2x when x is less than 0, and it's equal to 0 when x is greater than or equal to 0. Now that is a typical way that a piecewise function looks. And when you go to graph it, you start from way over there, negative infinity. And you go up to this point here. So everything between my field goals has to be 2x. And it has to go through the origin. So it's got to look like that. And then everything between my field goals on the right side of the y-axis is 0. So it's got to look like that. And I think that's probably, those two methods will cover anything you come across. Translating the elementary function or turning it into a piecewise function. Or the method you just stated. Fill in some x and y values and connect the dots.
Right. Yeah. Okay.
And that's only useful if you know the shape. In other words, if you know it's a straight line, you can do that. If you know it's a parabola, you can do that. You know, if I know I got a parabola and I got a dot there and I got a dot there and I got a dot way up here, well, I know that parabola is going to look something like this.
Right.
But if I know those two are in a straight line, well, now I know exactly what it is. So connecting the dots only works if you know the general shape of what you're graphing.
Right.
What other?
When it's an absolute value, it's always a straight line.
That's true. Absolute value is basically a combination of linear functions. It's always straight lines. So when you made your table last time, you should have had dots like this, and more dots there, and dots there. And now that allows you to graph it.
Right.
As long as you know those are straight lines, not curved lines. Give me another subject that you want to work on today besides factoring, graphing quadratics, graphing absolute value functions. You don't have any problem with inequalities, right? In other words, if I say y is greater than 2x minus 3, have you graphed that?
Well, I would solve first, like as if they were equal.
Okay.
So I put 3 on the left side.
Well, that's an mx plus b format. So,
oh no. So yeah, no. Then I would put my y-intercept, that's -3, and then I would use my slope for 2.
okay. So there's our line. Is it dotted or solid?
That line is dotted.
And which side of it am I going to shade?
You're going to it's greater than, so it's going to be
The
to the left.
The right side or the left side?
The left.
Trick question. Above or below?
Above.
That's the proper question. In other words, I'm only concerned about the verticalness.
Right. Because
I don't even look at it as right or left. I look at it as above or below. So all I have to do is find one point on the y-axis that's above that line. Pick any point you want. If it's there, that tells me which side to shade. Okay. What else? Give me some other subject material that's going to be on this test. I mean, you may have in our last session, but I can't remember right offhand what it is. What are the things you're doing? I can look at my book. It might help, but not necessarily because you might not be using the same book. Reducing radicals. It comes up.
Yeah, we covered that last time, but
okay, are you cool with that? That involves factoring the numbers. There's a couple of things to be on the lookout for when you're reducing radicals. Let me just warn you about them. How am I going to reduce that?
How are you going to reduce 32? Well, first you could start with
in fact, I'm going to give you a different one. I'm going to give you 80.
Okay.
It all depends on how you factor this. That's the first thing you have to realize is how am I going to factor that? If I factor that this way, that doesn't do me any good because neither of these are perfect square numbers.
Right.
So I got to find a perfect square number as one of my factors.
So 8 and 10. No, never mind.
Neither of those are perfect square numbers, yes. 4 and 20. Okay. That's going to work. It's not going to be the most efficient, but I'm showing you this for a reason. You get 2 root 20, but then root 20 can be factored.
2 can be taken out.
Right. It goes into 4 times 5, and that becomes a 2. That 2 times that 2. So my final answer is that, arrived at with maybe an unnecessary step in it. Notice that if I happen to notice that 16 times 5 is also factors of 80, so I'm going to write it this way. Boom. I'm there in one step.
Right.
So the moral of the story is that it doesn't really matter if you don't find the greatest perfect square factor. As long as you find one and start whittling the problem down, it'll always come down to the final answer. You don't have to break your neck trying to find the factor that involves 16. Although, it's useful to know your perfect square numbers. In other words, we're always trying, whoops, I left out 9. We're always looking for a factor that is one of these numbers. So when I'm looking to factor 80, 4 is a very common one. A lot of numbers are divisible by 4, but it's not divisible by 9. If I happen to spot 16 on my list or in my memory and I know, well, that's 16 times 5, then I'll get it there the fastest way.
Right.
What is this?
square root of 1/2 is, the square root of 1/2 is 1.
No. What's the first step when you have division going on inside the radical? Separate it out into the square root of 1 divided by the square root of 2. That's what I was doing, notice, before the first 3 problems. We basically had something, and I'm always separating it out into the product of those 2 things. Well, in here, before, it was 16 times 5. So I could separate it out into the square root of 16 times the square root of 5. Okay, well, same thing with division. You have division going on, you can change it. That's going to be equal to the square root of 1 over the square root of 2. Well, the square root of 1 is 1. Square root of 2 is an irrational number. So what do I have to do to this number to present it as an answer?
To present it as an answer, square it?
It's called rationalizing the denominator.
Oh.
And you rationalize the denominator by multiplying it by itself. Well, I have a fraction. I'm not allowed to do anything to that fraction other than multiply it by the number 1. So if I'm going to multiply the bottom by root 2, I got to multiply the top by root 2. And that gives me the proper mathematical answer, which is that. So that is the answer to that. And that's the only answer. You would lose points on you'd lose points on that, you'd lose points on that. I'm presuming that you've been taught that you can't have an irrational number in the denominator. In fact, you can't have an imaginary number in the denominator either. And if I had something like this, well, what do I want to multiply that by?
I over I.
Correct. In other words, that's going to turn the bottom into a real number, and that is the number 1. So that gives me 2i in the numerator, minus 1 in the denominator, or just minus 2i. So the process for rationalizing a denominator when you have an irrational number is very similar to the process of realifying an imaginary denominator.
Right.
All right. Let me continue looking through this chapter, and I'll probably find all of the subject material that you're working on. It does get into imaginary numbers, but you said you'd barely gotten into that, right?
For what? Imaginary numbers? Yeah, we didn't know.
Completing the square is in this chapter. This seems like the chapter you're probably using. Quadratic formula and the discriminant.
I mean, that's definitely not going to be on our test, but we can go over it.
No, don't want to. Let's just stick to what's going to be on your test until we feel like you're going to get an A+ on that test, and then we can cover stuff that you haven't covered yet. Let me look here. Linear equations, absolute X-intercepts, best fitting line. You haven't had to do that, have you? The line of least fit or least square. Linear regression is what I'm talking about.
No, I don't.
Okay. Got zeros of a function, square roots, complex numbers, completing the square, quadratic formula, discriminant, quadratic inequality, best fitting quadratic model. That's what's in this chapter. Sounds like that covers everything that your test is going to be on.
Yeah. The only other thing besides that is those those solution problems.
Okay. Let's do some of those. Question.
I think, honestly, right now, that's the thing that I'm having the most trouble with.
All right. My problem is going to be finding the problems, because this algebra book doesn't use that in this chapter.
Do you want me to post them up on the internet?
No, I can make some up, similar to the ones. The hardest ones I've found to do are the solution problems. but you can turn those into easy problems by merely turning it into a certain, volume of that thing. In other words, when we had a 40% alcohol solution and 50 milliliters of it, we knew what we had was 20 milliliters of alcohol and 30 milliliters or 30 liters of water, right?
Right.
So as long as you solve the problems by taking the thing that's being dissolved in the solution completely out and give it its own weight or give it its own volume.
There was a harder one that he gave us yesterday.
Can you find it? Let's do it.
I don't have the book. It was like I think I remember it actually. It was I don't know what the part of the car is called that holds antifreeze, but whatever that part of the car is called holds 300 milliliters of antifreeze.
Radiator. 300 milliliters of antifreeze, okay.
Antifreeze. And it holds that much only. So it says that right now you have 40% antifreeze in your radiator, and you need 50% for it to work correctly.
Okay.
You have 40% of 300 milliliters, and you're trying to get to 50% and you have to remove some fluid so that you don't go over the limit.
All right. So let's figure out how much antifreeze we have in the radiator right now.
So right now you have, it's going to be 120? Yeah.
Milliliters of pure antifreeze. How much do you want under your ideal scenario? Because it's freezing weather is coming and you want a higher percentage of antifreeze in there, so you want it to go up to 50%. How much needs to be added?
How much needs to be added?
Your radiator is only going to hold 300 milliliters of fluid.
You need 10% more if you were just doing pure antifreeze.
You're going to need 30 milliliters more. I'm going to want to end up with 150 milliliters of antifreeze. Right?
Right.
I'm still always going to have 300 milliliters of fluid. If I want that to be a 50% solution, then I better have 150 milliliters of antifreeze in there. Right now,
so I just have to drain.
Right now I've got 120. I need to add 30 milliliters of antifreeze, but there's no room to add it.
So you drain 30 and you add 30 of antifreeze.
Well, when I drain 30, I'm losing some of this 120.
Oh.
So let's see if we can figure out the equation. How much antifreeze is going to be in the entire system? Well, let's see. You know, I made a mistake when we did this problem last time. You know what it was? And it was a huge mistake. It wasn't a mathematical mistake. It was a mistaken approach. You should always solve word problems by beginning in the same way. Picking variables and defining them.
Okay.
Well, what do I know here? X is going to be, let's call that, what? Amount. What do we have to figure out here? We have to figure out the amount to drain.
Right.
That's going to be our first step. And does this presume that you have another bottle with 50% solution in it, or does it presume you have another bottle that's pure antifreeze? Because that matters.
No, yeah, you have another bottle. You have a bottle of pure antifreeze, 100%.
Okay. So, what do I want? I want 300 minus the amount that I'm going to drain to equal 150 milliliters. I want half of this to be 150 milliliters.
That's it?
No, that just tells me not much. What does that tell me?
How much you have to drink.
Well, let me think for a moment. If I multiply both sides by 2, I get 300 minus x equals 300. Minus x is 0. That's not my formula anyway. Thinking whether we need a second variable or not. That's what's tough about solution problems, is it's always a little tough to come up with the equation.
Right.
It was yesterday for me also, but the way I came up with it yesterday was actually picking some numbers and seeing if that didn't elucidate the problem. Let's do that today. Let's say I drain 100, and you obviously want to do this with the least amount of throwing away liquid. Let's say I drained 100 milliliters. Okay. So I would then have 200 milliliters left in the radiator, and it would contain 80 milliliters of antifreeze. It would no longer contain 120 because I drained some of it away. Now, if I were to add what I drained of pure antifreeze, then I'm going to have 180 milliliters of antifreeze. That'll be more than 50%. If I'm adding a solution that is something other than 40% or 100%, let's say it was a 70% solution. In other words, let's say I have the stuff that's in my radiator, and I have a bottle of stuff that's 70% antifreeze solution, not 100%. Okay?
Okay.
Well, now I'm only adding 0.7 times x, the amount that I took away, and that would give me 70 plus 80. Ooh. 150 milliliters out of 300, that would be my answer. So what did I do here? If I let x be the amount to drain, then I've got to solve for x. In other words, this is x. So my equation should be, not 200, 300 minus x. X is the amount I'm taking away. And then I'm going to add some fluid back that has a certain percentage of antifreeze. If it's 70% antifreeze, then I'm adding back that much. And that total is got to equal 0.4 times 300. No, it's 0.4 times 300 minus x. That's where I got my 80 from. Plus x times, doesn't make any sense. Actually, does it? Gives me 120 minus 0.4x equals 300 minus x. Might actually solve for it. Let me think here for a moment.
Wait, give me 1 second.
Sure. Go ahead. I'll be kind of thinking about this problem. Equals 300 minus x. So 180 would equal 0.6x. X would equal 30. Oh, we know the final amount of antifreeze has to be 150. So whatever equation I'm going to come up with has to equal 150. Well, I can do that. The amount of antifreeze we have has to equal 150. Well, if x represents the amount I drain, I got to multiply that by 0.4, because that's the amount of antifreeze I'm going to have after I drain x amount of it out. Then I'm going to add fluid that's pure antifreeze, and that has to equal 150. That's going to let me solve it. We get 120 minus 0.4x plus x equals 150. This is 0.6x equals 30, x equals 50. I need to drain 50 milliliters out and add 50 of pure antifreeze. Let's see if that works. Okay, if I drain 50 out, I'm left with 250 in the radiator. It's a 40% solution, so I have 100 milliliters of antifreeze. Now I'm going to pour 50 milliliters of pure antifreeze into that radiator, giving me 150 milliliters of pure antifreeze. So that's the answer. You drain 50 milliliters out and you replace it with pure antifreeze. And this was my starting equation. I know that I have to have 150 milliliters of pure antifreeze at the end, and my amount of antifreeze is 40% of my starting solution, which is 300 minus x, plus 100% of x that I have to put back in.
Okay.
Yeah, the trick on these solution problems is coming up with that equation. And that's twice that I had difficulty coming up with it until I experimented with some numbers. And the process of experimenting and trying some different values actually was what allowed me to state the equation properly. But if you think about it, this is the amount of fluid you have after you've drained some. It's 40% antifreeze. So we're going to multiply that by 0.4. We have that much antifreeze left. I'm going to add that much pure antifreeze. When I'm all done, I got to have 150 milliliters of antifreeze. There is an initial step, of course, which is to, if you desire a 50% solution, then you have to be able to figure out that that means that we need 150 milliliters of antifreeze in there.
Right.
Okay, once you have that figured out, now you can state this equation. And don't forget the first step, which is to define your variables. Very important. If you don't start off this problem by defining x as the amount to drain from the radiator to start, you got real problems. It's really hard to solve. If you
still
don't
pretty hard
begin it that way. I know, even if you begin it the proper way, it's still a difficult problem.
Yeah, we spent me and two of my friends who are doing really well in the class. We went to him for extra help because the midterm is next week and we don't really have class before that. So we went to him for extra help yesterday after school, and we spent at least 30 minutes trying to figure out this problem.
Yeah. Now, if the problem said that you can replace what you drain with only a 70% solution, then the only difference is that you're adding back this much antifreeze, 0.7 times x. You're still draining this much, but you're filling it back up with only a 70% solution. So this would give you a different answer.
Right.
If you're filling it up with an 80% solution, assuming you're filling it up with a 100% solution, pure antifreeze, then this number becomes 1, and we don't need it. So this equation is going to cover all of your parameters that he might have given you.
Right.
In other words, did he tell you that you have a 70% solution to fill it back up with, or do you have pure antifreeze, or is it only a 60% solution?
I mean, he told us yesterday that it was pure.
Okay. Pure actually doesn't make the problem as understandable as it would be if it was a 70% solution. Because it's not evident from looking at this that pure means a coefficient of 1 here. Whereas if I was filling it back up with a 70% solution, that makes a lot of sense. Plus 0.7 times the amount that we're going to put back in. So this actually would be a better problem to teach the understanding of the problem.
Right.
I think. I mean, just from looking at it, this sums the problem up very well. Whereas when I add x, it's not as clear that I'm adding x only because it's pure antifreeze.
Right. It should be x times like 100%.
Times its solution. Yeah, it would have been okay if he wrote it like this, 100% times x, maybe, and then convert the 100% to the number 1. So, yeah, it's a good problem.
Challenging.
Yeah. Now, I don't know if you've had problems other than solution problems. There will be problems like salt solutions, or not even salt solutions. Let's say you have a mixture of 50% gold, 50% silver, and you have 10 ounces of it.
Okay.
And you want to turn it into a mixture of 20% gold, 80% silver, and you want to end up with 200 ounces of it. How much gold and silver do you have to add? Those problems are a little bit easier because one tends to think of gold and silver as being a certain weight or amount, and they're solid. You don't tend to think of antifreeze as being solid or alcohol solutions as being solid, and that throws people a little bit. But if you think of them as being solids, that will make the problem easier. In other words, think of being able to separate that solution into a certain amount of antifreeze, certain amount of water. If it's a 40% solution, then 40% is antifreeze, 40% or 60% is water.
Okay.
And that's what we did in both problems, was consider both liquids as solids, basically. Solids with a certain volume, as opposed to solids with a certain weight. When you're actually dealing with solids, they tend to define them in terms of weight, not volume. Whereas when you're dealing with liquids, they tend to define it in terms of volume. And that's fine. I used volume in our problem. I had a certain amount of volume of antifreeze. I didn't know what its weight was. I didn't care.
Right.
Since it's all liquid, it's always going to be in volume.
It didn't matter.
Right.
Okay, so what should we do now?
It's up to you. You know, we don't need to go the whole 2 hours if you don't. I'll only charge you for what we do. In other words, if we stop right now, I'll charge this for an hour and 2/3.
Okay.
We keep going. If you have problems, it's going to be hard for me to come up with some of these word problems, solution kind of problems. But I'll do whatever you want to do. I can search my database and see if I can find some. Actually, you know, the interesting.
Well, the thing is, besides those, like besides what we just did, we just covered everything.
Right. So I'd say you're pretty.
So like I have a full understanding of everything. The only thing I'm iffy about is those mixes.
Okay. Here's what let me suggest. Let me suggest we end now, and between now and tomorrow morning, I'll find some solution and mixture problems. And we can spend however much time you want tomorrow on those.
Okay, that works for me.
It's liable to take me some time to find those, so it doesn't make much sense for me to, you know, waste 10 minutes of your time finding those problems. But I can find them and have them for tomorrow.
If you're gonna go find them, we could just charge for the whole 2 hours. You're gonna have to go and find them.
All right, I don't care about that. We're not talking enough money to even worry about it. But I'll just charge you for. I always have some outside time that you generally have to spend for every hour I tutor. I generally have to do some other stuff also, so I don't mind it. I'll charge you for 1 3/4. How about that? And then we'll do whatever amount of time tomorrow you need to do. But I'm pretty sure I have a set of these problems. Oddly enough, it's from an Algebra 1 class.
Okay.
That's odd, isn't it? Just another verification that every discipline in math starts out with the hardest level problems of the whole year.
Yeah.
For Algebra 1, it's solution problems. And that's the way they start out Algebra 1 students sometimes. For Algebra 2, it's linear programming. For geometry, it's proofs, 2-column proofs. For calculus, it's limit definitions, all of which are the toughest material you get in the entire year of each discipline, and they always start you out right away with it. That's why these solution problems that I remember I have on my computer, I'm pretty sure were from an Algebra 1 student.
Okay.
But that doesn't matter.
So on Monday night, that's 6:30. I don't think I'm going to be able to do that.
Okay.
So
let me go ahead and take that off right now because I will have people that will want that time slot. So I'm glad you said that. I'll go ahead and remove that.
And so if we need more time tomorrow, are you free after the class? I don't think we're going to need much more than an hour.
Yes,
so.
I am.
Okay, cool.
Right now I have you and only you tomorrow. Oh, no, hold on. I have a 3 o'clock, but I don't have anything right after you.
Okay, that's good.
Actually, I have a lot tomorrow. I didn't realize these got moved from earlier points in the week to this day. So, all right, Max, I will talk to you tomorrow at 10, my time.
All right. I'll talk to you tomorrow.
Bye-bye.